Okay, next talk is evolutionary optimization. Okay, so this is a talk actually is for 452, 552 when I teach topic. Likely we'll do it next semester, so I'm just going to give a very brief introduction to evolution optimization so you know that it exists and there's plenty of code built for it. Okay, it's built off these ideas in evolution that there's a population, that there's some mating or mutating might go on, that you have children, you have offspring, and then survival of the fittest. So we're going to use those ideas. It makes sense that a population will be solution members. So back to our, let's go back to Rarden with our linear programs, right? We had some X vector, X1, X2, X3, let's say. We're trying to find those variables. We can create an X vector. Maybe there's 5 different X vectors we're going to start with. We put them all together, append them, and we have a little matrix here that is a population matrix. Each column is a member of the population at that iterate. We can think about that like when we did the hill climber, where we dropped some parachutists, drop 5 parachutists down onto your feasible region. They land somewhere, that point, each one of those points is a solution vector. That'll be the initial population. Now you could take some members of the population, you can make them mate. We'll talk about how you do that. What does it mean to mate for a particular scenario? Or you could take one member and mutate it. Again, let's just wait for an example. You can have reproduction that's like, rather than just 2 parents, you could have 3, 4, 5 parents, however many you want. You could create more than one child. You could have twins, you could have triplets. And what you're going to do is decide with that population, there are 5 members of the population. You're going to decide which are the best, which are the fittest by function evaluation. So again, think about that. Parachutists come down, they land, they report their function evaluation. So they give, here's my objective function value. Some are better than others. The weakest, you're going to leave the population, and maybe you'll mutate the weakest because you're just going to randomly move things. The best, you'll probably mate. And then you'll have a new population at the next iteration. Right, so we're actually going to do that on one particular application here. That's a problem I've worked on often, and this is from a master's thesis of a student of mine, a colleague, Catherine Petings-Bailing. We work on a problem called ranking or rankability. We're trying to rank items. And so a very simple example to think about, this could be ranking anything, but let's say we had teams that scored against each other. So like team 1 beat team 2 by 5 points. Team 1 beat team 3 by 10 points. Team 1 beat team 4 by 15 points, and so on. Well, if it happened that these were the scores and this is what actually happened, this is what we called perfect hillside form, because when you did a city plot in MATLAB of that, it looks like this little cubert, looks like hillside. But if this actually was the game data, who played who, and these are the scores, we can say that's easy to rank the teams. It's first, second, third, fourth, right? It's very clear that team 1's the best. They beat everybody, and they beat team 2 by a little bit, team 3 by more, and team 4 by the most. So team 4 must be the worst. If something's in perfect hillside form, it's a diagonal matrix, and the rows are increasing, the columns are decreasing. So we made this definition of what something was hillside, and then we were trying to say how close is a particular data set. A data matrix of game scores, they don't look like this usually, but could they be reordered to be close to that? And if they can't, how many violations do we have? So yeah, again, the perfect sports season is a hillside form. We want to reorder a given data matrix of who played who, like Duke played UNC, College Charleston played Davidson. What was the score? Can we symmetrically reorder the rows and columns so that what we get is perfect? Very unlikely, never happens. I think I had a colleague that did this for like all the college football seasons for the past 20 years, and it only happened once that there was a perfect season, perfect hillside season. So uncommon, but for those other years where they're not perfect, were they close to perfect? Were they terrible? Were they a mess. If it was a season that was really terrible, then we'd say that's kind of not very rankable and we shouldn't trust. It's going to be a wild like conference tournament. It's going to be a wild March Madness season. Okay, so part of what Catherine's thesis work was to count the number of violations. Like if this was what we got, if this was the matrix that was given, because this one outscored this one, we'd say that's a violation. And same thing here, like we want them to be increasing across the rows, decreasing across the columns. They're not. Anybody that's in the lower triangle, there's also an upset. Like this says the third ranked team beat the second ranked team, and that shouldn't happen. Whereas we say these ones here, we call those weak wins. Like they won, but just not by as much as we thought they should have. So in evolutionary optimization, we can actually cast that whole ranking problem as an evolutionary optimization. We want to find a ranking, a permutation vector of our teams that minimizes the number of violations that happen. So given a D matrix, we want to get just randomly pick a ranking, 1, 2, 3, 4, 5, let's say. That creates a D matrix. We go in and count how many violations there were. But suppose it had been the ranking 2, 1, 3, 4, 5. That would create a different D matrix, which had a different number of violations. So the number of violations is actually our fitness score. And we want the one that has the minimum fitness score. All right, so this picture here really summarizes Catherine's work. She did this in a nice poster and then also put in her thesis. Each column here is a member of the population. For us, a solution vector is a ranking vector. So 2, 4, 1, 3 is a ranking. It says team 2 is the first place, team 4 is the second place team 1 is the third place, and team 3 is the last place. Each column, in this case, is a solution member. Back to Rardin stuff, this might be an x1, x2, x3, x4. Maybe those are values between 0 and 1, decimals or something, so 0.5, 0.7, 0.2, 0.9 or something. So those are just your solution values. But for us, each solution vector is a ranking. All right, so she had this initial population. For each column vector, each ranking gets a fitness score. Again, just like we talked about counting how many violations there were. So every one of these has an objective function value associated with it. You take the ones that had good objective function values and you make them. So you make, let's say the first one might have had a good objective, the solution vector had a good objective function value, and so did the next one. So Catherine mated them. How do you mate them? Well, we'll talk about, there's plenty of ways of doing that with permutation vectors. And for whatever your application is, usually you can say, okay, how would I mate these to come up with a good child? She made just one child. Let's see, she took the third one and mutated it. Maybe they had a really low objective function value. So she just did some sort of mutation. Things you could do are just flip the vector. Things you could do are take some subvector and flip that. You could just take 2 items and flip them. You could take some chunk out and put it somewhere else. So if the fitness is bad, you're going to go back, do another iteration. If the fitness is good, you're going to keep that guy. And so the population will change. This is your next iteration. And you stop when the population has changed very little. So if things are starting to look the same and you print out the best, the one that has the best objective function value, you say that's the best ranking. Here's just one example of a way to do a mating, something called a border count. You can take, and border count takes however many parents you want and spits out a child that is sort of the aggregate of those. So these were all good scores, well behaved, and they make a nice child that has properties of those. Like for instance, many of them had 1 towards the bottom, so does the child. Many of them had 3 and 5 towards the top, so does the child. You could mate with another algorithm called average rank. So that was part of her thesis. She talked about different ways of mating, mutating. She just flipped the, sections of 5 and 2. She flipped just 2. She identified I and a J, and then she flipped those elements. Insertion, displacement, reversal. So lots of different ways of doing mutating, the idea with mutating is this, you're injecting randomness into the system so that you can escape a local min. EO, the reason it's so cool, and again, we'll probably talk more about it in 452, 552. It's really like the Swiss Army knife of optimization. Pretty much any problem you can think of, you can cast in this way of what's a member of the population, how do I make good ones, how do I mutate bad ones, and doing that iteratively. It can handle really large data sets, any type of problem. Given enough randomization, you're eventually going to escape a local min if you just let it run forever, run long enough. Very simple structure. You can design it for pretty much any problem, although it can take a long time to get to that min. And you can get stuck in a local optima for a very long time. That's the importance of the mating. How often do you mutate? How often do you mutate versus mating? In deciding, do I take 70% of them and mate them, and then the bad 30% mutate, or what's the ratio there? And how random are those mutations? And because of randomization, identical runs might give you different solutions, and that can be hard when you're building an algorithm and testing it. And for that class, we actually had the live in that class, had the students say, okay, could you do an EO to solve AX equal B, a linear system? Y'all are familiar with linear algebra. There's a way to do that. X vectors, just if this is a, say that A is 4 by 5, and then X is 5 by 1. Well, population is just a 5 by 1 vector. There's no constraints on it. So just, any components in there, just randomly generate an X vector, randomly generate another one, maybe put 5 of them in a matrix and call that your population. How do you measure the fitness? Well, X will be a good solution, well, an actual solution, if it solves A times that vector equals B. How close is AX to B? So you take a norm of B minus AX, and that's your fitness. And then you can define different mating, mutating, and you're there. Well, there's another thing called a Markov chain. Again, we'll learn about that next semester. You could solve Sudoku puzzles. You had to do some work on Sudoku puzzles. You could think about how to do those as an evolutionary optimization. You could solve the traveling salesman problem as an EO. So again, almost anything you can think of, you can fit into this framework. Okay, we'll stop there. EO, the Swiss Army knife of optimization.